Hi everyone. In this section, I'm going to speak about differentiation rules and integrals of vector function. First, we start with the differentiation rules for vector function. Derivative of vector functions may be computed component by component, so the derivative rules for vector functions are similar to the derivative rules for scalar functions. Look at this here. If u and v are differentiable vector functions of t, capital C is a constant vector and C any real number or scalar number. And suppose f is a differentiable scalar function. Derivative of constant vector is equal 0. Derivative of C times u, C as a scalar number, is equal to C times derivative of u, or derivative of f times u is equal derivative of f times u plus derivative of u times f. The next one, derivative of u plus v is equal to the derivative of u plus derivative of v. Difference rule is similar to the last one. Derivative of u dot v is equal derivative of u dot v plus u dot derivative of v. As you know, dot product is commutative, so we can commute these two functions. Derivative of u of t cross v of t is equal to derivative of u cross v plus u cross derivative of v. As you see here, since u is the left side function, we can't change its place when we calculate the derivative. The last rule is chain rule. Derivative of u of f of t is equal to derivative of f with respect to the t times derivative of u with respect to the f of t. Look at this example. Suppose r of s is a vector function and s is a scalar function. To find the derivative of r with respect to the t, first we find derivative of s with respect to the t times derivative of r with respect to the s. Okay, derivative of s with respect to the t, derivative of t cubed is 3 times t squared minus derivative of t squared is equal to 2 times t times derivative of r with respect to the s. Derivative of e to the s is itself. Derivative of ln of s is 1 over s, and derivative of square root of s is 1 over 2 times square root of s. Now we can multiply this scalar function into the vector. So we have 3 times t squared minus 2t times e to the s, 3 times t squared minus 2t over s, and 3 times t squared minus 2t over 2 times s squared. Finally, s can be replaced by t cubed minus t squared. Next part is about vector functions of constant length. Suppose this curve is a particle's path moving on a sphere centered at the origin. At each time of t, the length of r of t is the same. If r as the position vector is differentiable, derivative of r with respect to the t, which is called velocity vector, is tangent to the particle's path. So it is tangent to the sphere. Therefore, velocity vector is orthogonal to the r of t at each time of t. We can prove it easily. As you know, r of t dot itself is equal to the magnitude of r of t squared. Since at each time of t, magnitude of r is constant, so it is equal to the c squared. By differentiating both sides of this equation, the derivative of left side is equal derivative of r with respect to the t dot r plus r dot derivative of r with respect to the t is equal derivative of c squared is equal to 0. Since dot product is commutative, so we have 2 times r dot derivative of r is equal to 0. Therefore, r dot derivative of r with respect to the t is equal 0. That means r is orthogonal to the derivative of r with respect to the t. Therefore, if r is a differentiable vector function of t of constant length, always we have r dot derivative r with respect to the t is equal to the 0. The next part is about integrals of vector function. Suppose f of t is a differentiable vector function. We say f is an antiderivative of r at each point of this interval whenever derivative of f with respect to the t is equal to the r of t at each point of this interval. Now, indefinite integral of r is the set of all antiderivative functions. Therefore, indefinite integral of r is equal to f of t plus c, in which c is a constant vector. Look at this example. We have integral of cosine of t I plus j minus 2 times t k with respect to the t. It is equal to the integral of cosine of t dt I plus integral of 1 dt j plus integral of negative 2 times t dt k. Integral of cosine of t is sine of t plus c1 I. Integral of 1 is 2t plus c2 j. Integral of negative 2 times t is negative 2 times t squared over 2, of course, plus c3 k. Therefore, it is equal to sine of ti plus tj plus negative t squared k plus c, in which c is equal c1i plus c2j plus c3k. The next part is definite integral. If r of t is equal f of ti plus g of tj plus h of tk. If the components of R are integrable over the closed interval like this, so the integral of R is definable from a to the b and is equal to the integral of f of t with respect to the t from a to b I plus integral of g of t dt from a to the b j plus integral of h of t dt k from a to b. At the previous example, as you see, integral of cosine of t I plus j minus 2 times t k with respect to the t from 0 to pi. We have sine of t from 0 to pi I plus t from 0 to pi j minus t squared from 0 to pi k. Sine of pi is 0 minus sine of 0 is 0 to I plus pi minus 0 j plus negative pi squared minus negative 0 squared k. Okay, these two sentences are 0. We have pi j plus negative pi squared k. Okay, here is the end of this section. See you soon.